All right. So what we're going to do is we're going to go through some practice problems of some stuff that you might see on the exam. So here is one of the problems. I'm just going to draw it out. And what you're going to see is we have an OH, so an alcohol group. And then we have something which is NaNH2. And in the second step, we have a benzylic bromine. So this is a predict the products question. And how we would go about solving this is we have to think about what does this do? And what you'll see is that Na is a plus charge, meaning that the NH2 is going to be a minus charge. And we see that this is actually going to be a strong base. Strong base is going to come along and deprotonate the proton from the alcohol, just slightly acidic. So the pK of an alcohol is about 16. And now that we have this, we're going to have an O minus. And we have a O minus, which is a good nucleophile. So in step 2, we have Br, which is a good leaving group. So we can actually do an SN2 reaction. And we will draw the product here, which will be a ether. And remember always to count carbons, 1, 2, 3. So 1, 2, and 3. So generally for these kind of questions, they want to see that you can recognize that this is a base, and then what will happen when we form, for example, a nucleophile in the second step. The key thing that you want to watch out for here is stereochemistry. Notice how in this case, because it's a primary, we don't really care about the stereochemistry, but for example, if it was a secondary and there was some sort of stereochemistry, we would have inversion via SN2. All right, the next question we're going to go over is very similar. And it's going to be with a give me 1 second. Pen is bugging out. Right. So the next question we're going to do is we're going to have a phenol, which we know is slightly acidic. I believe the pK of a phenol is about 10. So this should be in your pKa table, and this is something that you should know. So we have NaOH, and we have a epoxide group. So generally, when we have an epoxide group, this is a common question they like to throw in. And then the last step is going to be workup/acid. So whenever they have an epoxide, they just want to see that you understand how the reaction works. So if we're going through an SN1 pathway, you'll want to form the better carbocation. If you're going through an SN2 pathway, you want the less sterically encumbered side. So we have to decide whether this is SN2 or SN1. Again, we're going to see that Na is a plus charge and the OH is a minus charge. Meaning that this is basic conditions and we're probably going to be doing SN2. Again, we'll come in with the first acid base step, which is to deprotonate the hydrogen, and we form the O minus species, which is resonance stabilized or aromatically stabilized. Now that this can come in, it can actually come in and do a SN2 attack. So notice how we have 2 spots to do an SN2 attack. We have over here and we have over here. This side is more sterically encumbered, so that side would be better for an SN1 reaction. However, this side is less sterically encumbered, so it would be better for an SN2 reaction. As a result, when we do our attack, we're going to see it comes in from this side, and we have O, and we're going to have the ring open up. Now, the key thing to note here is that the stereochemistry is not provided. However, if it was provided, there would be some sort of inversion. But I think this question, that's sort of beyond the scope here, and it's not that important to look at that. All right, the next question is going to be a mechanism question. Again, very similar, sort of going through these sort of SN2 reactions, which are under basic conditions. We want to see that we have something that looks like this. And we have NaNH2. So whenever you see something like NaNH2, you should immediately think, okay, this is a base. It's going to do my deprotonation. And you want to look out for an acidic proton to deprotonate in the first place. All right. So we have this. And then again, yeah, we're going to have a workup. So if you don't know what a workup is basically just acid to neutralize the species and give it its sort of final product. So we have our Na plus. Again, we have our NH2 minus. And this is going to come in and actually deprotonate the hydrogen on a terminal alkyne. So the terminal alkyne pKa is about 26. And we'll see that we form a nucleophile. And this nucleophile can actually come in and attack this sort of oxygenated group, sort of epoxide type of thing. So we're going to, again, come in on the less sterically encumbered side. This side has too much steric hindrance. It's actually tertiary carbon, which we know can't do SN2. So when we're drawing our mechanism, we want to indicate that. And what we're actually going to see is because it forms one bond, we actually have to break one bond to keep our sort of formal charges. Remember, carbon can only make 4 bonds. And once we sort of draw the next step, again, we want to include our arrows. And we will see that we have something that looks like this. Okay. So that is sort of the key point here. And then the last step, like I said, workup is just going to be some form of acid. Generally, it's H3O plus, or whatever acid or whatever proton species will allow us to get to our final product. And we get to our final product, which is going to be neutral. So we'll redraw the species, and we will see that we have our alkyne now with the alkylated group. And it looks like this. So whenever we're drawing a mechanism, SN2 is quite simple. It's just going to be, normally we form some sort of nucleophile by doing an acid-base reaction, so deprotonation. And then the nucleophile is going to attack the electrophile in some sort of way. And then if we need a workup, we'll do a workup, which will just sort of neutralize things. Another sort of question that we're going to be working on is, let's check this out, let's see. Is we're going to do a question regarding aromaticity. And what we'll see is that it says, which of the following compounds is likely to adopt a planar conformation? So for this question, it's going to be related to hybridization. And what we'll see about hybridization is, we'll see for this one, take a look at it, we're going to have sp2 all around. However, this is not aromatic. Not aromatic. And what's that called? This is actually a very weird example. We'll get to that at the end there. What we'll see here is this is going to be sp2 all around. And we actually have 6 electrons. So this will go over here. And then this can go here, and we can replace that. So we'll actually see that this is going to be planar. Let's take a look at this though. Notice how this nitrogen has no lone pairs. So it's actually stuck in an sp3 conformation. So it's not going to be planar. And then this lastly, this sort of, so this is aromatic. And if we look over here, it says it can't be planar. So the problem with this one is, we'll see why. It's because we're going to have hydrogen sticking out. And if you imagine drawing a plane with this shape, we're going to see that the hydrogens can't really point in the same direction. So it won't be in the plane. It'll actually kind of be twisted. Okay. So this is, again, going to be another question related to aromaticity, which is going to ask us, which of the following is most likely to lose water upon protonation with HCl? So this is a good question because they want to see that you understand how aromaticity works. So rather than sort of just guessing and checking, what you should do is you should draw all of these groups as if they're losing H2O. So I'm just going to write H2O plus, right? And then what we're going to do is we're going to imagine all of them leaving. Hello, I just saw somebody joined. If you have a question, feel free to ask. I'm just going through a practice problem right now. So let me just finish this problem and then I can get to your problem. So what we're going to see is that if we draw the species without the water, we have a plus charge here, we have a plus charge here, we have a plus charge here, and we have a plus charge here. So if it's asking us which is most likely to lose water, we want the one that's the most stable. So if we ask ourselves, this right here, it's not a conjugated ring, right? So this is sp3, so that's not aromatic. Here we have 4 electrons, so it's not aromatic. And here, there's a plus charge on the double bond that's very bad. We don't want that. So actually we're going to do this one because we'll see that's actually aromatic. So notice how after it loses water, it's going to be aromatic, which is good. It's very stable. So that means that this is the most likely to lose water after its protonation. All right. So I see that Leo has joined the chat. So feel free to ask your question over the chat, or you can send it in the Discord and then I can pull it up. Did you have any particular questions, or did you just come to sort of do the review questions? Let me know in the chat. No particular question? Okay, cool. So what I'll do is right now I'm just going over review questions. Is there a particular topic that you want to go over? Or do you just want to follow along with random questions? Just let me know in the chat. Go as you may. Perfect. Cool. All right. So a very common question you're going to get on the 233 exam is going to be a question that looks like this. And they always like to do this. I think all the past midterms have a question like this. So just straight off looking the bat, it says, explain why the reaction shown affords only a single addition product upon treatment of HBr. In your answer, you need to explain by illustrating the intermediate formed in the reaction and why none of the other double bonds in the starting material react, and why the bromine adds to the carbon indicated in the scheme. So what we're going to see about this question is, first of all, whenever we have a alkene and we add an acid to it, we'll see that it can either add to this side or it can add to this side. And then if we add it to this side, sorry, if we add the hydrogen here, then the bromine is going to come in and attack from here. However, if we add the hydrogen to the other side, over here, we are going to see the bromine come in from the other side. Okay. So right off the bat, do you want to try giving this question a shot before I answer it? Or do you want me to just go through it? Also, I just saw somebody else has joined the chat. Just feel free to ask a question. You can send it to me over Discord, or right now I'm just going over review problems. So if you want to just follow along the review problems, you can as well. If not, feel free to send me a question over the chat or over the Discord. Did you have any particular questions, Nathan?
No, I just clicked the link and
okay, cool.
Yeah.
So right now we're just doing a quick review problem. So here's what I'm going to do. Do you guys want to give this one a quick shot and then I can go over the solution? Just let me know in the chat if you guys want to talk. What do you guys think? Do you guys want to try out this problem? Okay, so he left. So I guess I'll just go through this problem with you. So what we're going to see is that the hydrogen can add to two sites. Okay, we can add to here. Sorry, we can add the hydrogen here, or we can add the hydrogen here. Now you might be wondering, okay, why can't we add the hydrogen here? Well, the reason is because this is an aromatic system, so it's quite stable, and we don't want to add to it. So now we have to consider, okay, if we add it here, or if we add it here, what are the two different sort of products we're going to get? Or sort of the two different intermediates we're going to get. Yeah, no worries. And what we'll see is we'll be able to get two different things. One with the carbocation here. And one with the carbocation here. So which do you think is more stable, the left one or the right one? If you don't want to answer, you just want to watch, that's fine. So what we're actually going to see is the right one is going to be more stable. Now, why is the right one going to be more stable? Well, the right one's going to be more stable due to resonance stabilization. So we'll see that we can have a resonance over here. And this resonance species is going to be stabilized by the aromatic system, which is going to look like this. Oops. And what we're going to do is we're going to have a delocalization of this positive charge in this ring, which means that this is actually going to be the more stable species, which means that if you think about how this reaction works, it's a hydrohalogenation reaction or acid catalyzed addition to an alkene. We'll take this minus charge and it's going to add to this position, hence why we get this. So in our explanation or rationale, we'll say that this intermediate is more stable due to resonance. Slash aromaticity. All right. I'm going to put this on pause real quick. I just need to get an ice pack for my computer because it's overheating. All right, I'm back. So we're going to go through another practice problem. So the key point in this practice problem was realizing that aromaticity and resonance is involved. So whenever there's a question in 233 where they ask you, why does this happen, et cetera, generally it has to do with resonance and aromaticity. Those are the two main key steps in 233. All right. So here's a simple stereochemistry question, and it's basically going to ask us about the relationship between the following molecules. And what we're going to see here is, if we take a look at this, you might be tempted to say these are enantiomers because they are inverted centers. But what we're going to see is that if we rotate this bond, we're actually going to have something that looks like this. And what you'll recognize right away is that this is a meso compound. And whenever we have a meso compound, it is actually achiral, which means that both of these are the same molecule. And so we'll put in same for same molecule. Over here, we have two chiral centers and only one differs. So this is going to be diastereomers. And over here, we have two chiral centers and both of them are inverted. Therefore, they're going to be enantiomers. So that's a quick way of how you can determine what the relationship between the molecules are. All right, let's see. So here's what we're going to do. We're going to go through an SN1 type problem. So in 233, this other product isn't going to be covered. This is a rearrangement product, so you don't need to worry about that. In 233, we can ignore rearrangements. So what we're going to see is that we have an acid addition here, and it says SN1 conditions. So we're going to expect an SN1 product. Right off the bat, we look at OH. Is it a good leaving group? OH is not a good leaving group, so we have to convert it into a good leaving group first. So we'll take the oxygen and protonate it using HBr. And what we're going to see is we have OH2 plus, and we have this. Now, if we take a look at this species, we're going to see that OH2 is actually a good leaving group. And when OH2 leaves, we're going to have a positive charge, a carbocation. And when we have a carbocation, the nucleophile now, which is going to be Br minus, can attack, right? And when we do this, we're going to form this bromine product. And that's sort of the simple mechanism of SN1. Remember that we need to have our leaving group leave. So right off the bat, OH by itself is not a good leaving group. So before it leaves, we have to convert it into a good leaving group using the acid. And then once it leaves, we have a carbocation that can now be attacked by the nucleophile. All right, so the next problem we're going to take a look at is, let's see. All right. Okay, so I'm pretty sure this popped up on the a very similar problem popped up on the final in 2019. So this was a very good problem. So let's go over it. So what we're going to see is that we have some sort of ring cyclization. And how are we sort of going to go through this? Well, let's think about what happens when we add an acid to this alkene. We're going to have H3O plus. Right, this is going to be our chosen acid because it's in water. And the H2SO4 is a catalytic acid, which is going to form our hydronium ion, or our basically acidic water. And the pKa here is about -2. So when we have this, what we're going to do is we're going to form the more substituted carbocation, which is going to be this one. And what we can see now is the alkene can actually come in and attack. And what we have to do is we have to count 1, 2, 3, 4, 5, 6. So we form a 6-membered ring here. And we will draw our 6-membered ring. Now we're going to have a positive charge. And our positive charge is basically going to be now attacked by some sort of nucleophile. So we look in our solution and we ask, okay, what nucleophile do we have? Well, H2O is actually going to be a good nucleophile, which can come in and actually attack our species. So we take our H2O, come in, we attack it, and we move on to the next step, which is going to be OH with a plus charge. And now we can sort of see that, okay, we want a neutral species. So what we're going to do is we're going to take some sort of base. Notice that water can actually act as a base to itself. So it's going to come in, deprotonate that, and we're going to form our alcohol species, which is the product. In this case, it's not drawn, but you should understand that because this is a carbocation, in this step, we're actually going to form 2 products. One can attack from the top and one can attack from the bottom. Over here. So we're going to have one which looks like this, and one which looks like this, which the dashed lines. Sort of that's the key step to recognize that problem. All right, what else shall we go through here? All right, so what we're going to do is we'll take a look at another sort of acid type question. And what we'll see is that generally there are patterns when we're doing these kind of questions. And we'll see that we have to protonate something, which causes something to leave. And then when something leaves, we can form another bond, et cetera, et cetera. So what we're going to do here is we're going to think, okay, we have some sort of acid. And we think, okay, this OH clearly disconnects. So we're going to just add this to some acid. And what we're going to see is that once we add this to acid, we're actually going to have a plus charge on the oxygen, which is actually going to allow this bond to leave. And then once we allow that bond to leave, we'll be able to see that we form a tertiary carbocation. And then whenever you have a tertiary carbocation, we can actually form a alkene attack. Once we draw that, we're going to get a 6-membered ring. And we should have something that looks like this. So at this point, what we're going to see is that we have a plus charge over here. And I don't know if you guys have gone over this yet, but this is going to be an E1 reaction to actually finish this off. So actually, I think this will not be covered for the first midterm, and we'll get to this product. So the sort of key step here is whenever you're provided with a reagent and a product, they want to see that you understand the mechanistic rationale or the sort of steps you get to the finish line. Notice how here in the product, the OH is by itself, or the oxygen group is by itself and is not connected to anything. So that kind of lets us know that it's going to get disconnected. And if you think about just by itself, it can't be a leaving group by itself because we don't want an O- in a basic condition. So instead, before it leaves, it has to get protonated, and then we form the carbocation, and then we add to it. All right, sort of that is the sort of key sort of step with these sort of reactions. All right, what I'm going to do is I'm going to go on a quick break and come back with more problems in just a second. All right, here we want to take a look at the relationships again between stereoisomers. So what we're going to see is we take a look at this one first, and we'll see that the BR can actually be rotated. If we rotate it like this to take the CH2, CH3's position, and the H will actually be able to take the, actually, sorry, a better way to rotate it would be to sort of rotate it in the plane of the page. And we'll see sort of right away that this is kind of a internal mirror plane, which will sort of give us this coming out and the H going back in. So imagine you had a pole down the middle, and we would see that these two things are actually the same. So they're going to be identical. For the next one, we're going to see we have one chiral center, which is going to be inverted. And whenever we invert all the stereocenters, that is what we call enantiomers. All right. So now we're going to have something that looks like this. And we're going to see that the OH is connected to a completely different place. Here it's connected allylic. So it's one away from the alkene. And here it's connected on the other side. So these are what we call constitutional isomers. Right. And then here we have a Haworth projection. And what we're going to see is we want to be able to draw the other one, this one, in a planar formation. So when we do that, we're going to get something that looks like this. So how do we arrive to that? Well, we can see that this sort of front methyl group is going to be pointing upwards. And for it to be pointing upwards, we have it that looks like this. And then we have the OH going into the page. So this would be going into the page. And then obviously the hydrogen would be sticking up. Then we have the OH, which is going to the left. So it's going to be sticking out of the page. And then the CH2OH is going to be in the same plane as this methyl group, right? Because we can see that these two are anti. You can see that these two are anti, which is going to be that group. So if we take a look at this, what we're going to see is that this is actually going to be the mirror image of this, which is the non-superimposable mirror image, which is what we call enantiomers. All right. So what we're going to see here is we're going to see a chair flip, or sorry, not a chair flip, because if we were to flip the chair, or if we did a chair flip here, what we would see is this I would now go, if it's going up, it's going to look like this, it's going to be equatorial now. And this one, which is going down, is going to be down on it's going to be down on axial. So it should be, that's axial. Right. Okay. So for this one, I guess we can just tell that these are sort of two different chair structures. One's going up and one's going down. So this is going to be cis and trans. This is going to be cis and this is going to be trans. So cis and trans are isomers and they're actually going to be diastereomers. Cool. Right. Yeah. Newman. Yeah. Sorry. Newman projections. Thanks for that. Yeah. Okay. So what we're going to take a look at now is we can discuss some sort of acidity / basicity trends. So a really common question that you're going to get in 233 is whether something is acidic, whether something's basic, or we want to judge the equilibrium. So let's talk about that. So it says circle the strongest base in each set. So for the first one, what we're going to see is we have three sort of types. Here we just have carbon-carbon bonds, which aren't going to be very good. Here we have carbon-nitrogen bonds, and here we have carbon-oxygen bonds. So we're going to draw the two different structures here. If they were to be protonated, because remember, if it's a base, it's going to get a proton. And what we will see is that nitrogen is a lot better at handling a positive charge than oxygen because nitrogen is more electronegative. Therefore, this is going to be a stronger base. Now we look over here. This has a plus charge. This is neutral. And this is actually going to be negative because CH3O minus and Na plus is an ionic bond. So this is going to be our strongest base. We're going to do the same thing now with acidity. So basicity and acidity are quite related. It's just that when we're evaluating basicity, we add a proton, and when we're evaluating acidity, we remove a proton. So notice how here, right off the bat, we can see that if we remove a proton, this O minus like this, which is actually going to be aromatically stabilized through resonance. This has no resonance. This doesn't even have a proton. We have these protons, but these are very bad protons to take because they're in part of the aromatic system. And here we do have protons, but this is already an O minus, so it's not looking too good. So it looks like this will be the best acid. Also, another thing you can sort of realize is that OH, phenol in this case, is actually going to have a pK of about 10. pK of a regular alcohol is about 16. This we won't even have pKs for, so they're not even acidic. Next, we're going to be looking at this, which has to do with hybridization. So it's quite common where they sort of want you to see which is the strongest acid. And we'll see that the more S character something has, the more acidic it's going to be. So the answer is going to be the alkyne, because alkyne, alkyne is going to be SP. Alkene is going to be SP2. And the other one, which is just going to be a methyl, sort of a methyl group, or like alkane, is going to be SP3. And what we'll see is that this has 25% S character because there's 4 things in total, right? 3 p orbitals and 1 s orbital, so it's going to be 25%. Here we're going to have 33%, and here we're going to have 50% S character. So the reason why it's good is because when you have S character, after we deprotonate it, we're going to be left with a negative charge. And how do we stabilize negative charge? What we'll notice is an S orbital with a positive nucleus is better at stabilizing a negative charge. However, if you think about a p orbital, where the positive charge is, we can't even have the electrons there. So it's not as good at stabilizing the negative charge. So oftentimes we want more S character, and the more S character we have, the better it is at stabilizing sort of a negative charge, for example. Okay, so what we're going to see now is we have 3 different options. So here, if we deprotonate it, we have this. Here we have a NO like this. And then this, we're going to have something that looks like this. So what we're going to see is that this, through the inductive effect, is actually going to draw away sort of charge from this carbon, which isn't good, right? It's going to destabilize that. We want it to be stable. Here, however, we can see that this has a lot of resonance. This is pretty good at donating. This is pretty good at, this whole thing is going to work together to destabilize this negative charge or stabilize the molecule through resonance. So this would be the answer for this one. You're missing a carbon. Where is I missing a carbon? On here? Yes, I believe I am missing a carbon. Right. Thank you. Yeah, thank you for that. There we go. Okay. So what we're going to see here is basically going to be the inductive effect. So if you think about this, so this inductive effect was actually good because we're thinking about it backwards, right? because when we're talking about acidity, we want the conjugate base to be stabilized through the inductive effect, right? So this negative charge is going to be here. Which is going to have our O minus here. And because this electronegative element is close to our sort of negativity, it helps to stabilize it. And over here, this is even more of an inductive group. So if you draw the resonance structure for this, it's actually going to look like that. We'll see that because there's a plus charge on the nitrogen, it's quite electron withdrawing. So this group is actually going to be a very good inductive group, which to steal electron density. Does that make sense? Yeah, sorry, I forgot the carbon there. All right. Do you have any particular questions? I mean, I don't mind going through more problems, but we can just, if you have any particular questions about the course or anything you want to ask, you can feel free to. All right, no worries. I think the biggest thing you want to look out for this exam is going to be the SN1 versus SN2. Some of the multiple choice questions can be a bit tricky. They might ask you, will this happen, or et cetera, et cetera. Generally, the thing you want to look out for is, for example, when you have sp3, so an sp3 carbon, SN2 never happens. However, maybe it'll happen like 1 out of like a billion molecules or something. It'll happen, but we count this as never happens because it's so unlikely. So because there's trillions and billions of molecules in the flask, technically a lot of reactions happen, but because it's actually going to be a statistical kind of argument. So whenever this sort of pops out in the test, people say, oh no, but like this does happen sometimes. Sort of just realize they mean on like, okay, a statistical average, what's actually going on. All right, I think we have time to do a few more questions and then can go through it. All right. So for this question, they want us to fill in the reagent and to draw the mechanism. So do you have any ideas? Oh, okay, you got a question. What's up? You can send it to me on Discord. The difference of pKa between a ketone and an ester. Okay, let me just double check. So pKa, ester. Let me just double check the pKa's again so I can see. Do you happen to know the actual number? Forgot the number. pKa is about 25, I think. Okay. So the pKa is a ketone, and this is an ester. And I believe this is about 25, and a ketone should be about 20, right? pK of a ketone is 20. Let me double check. 20 and 25, perfect. Okay. So why don't we draw out the dipole moment here? So what we're going to see is we have a dipole moment like this, and we have a dipole moment like this, right? The oxygen is going to be stealing electronegativity. So if we were to draw a resonance form of this, what we're going to see is we have an O minus and a plus charged carbon. And we have O minus again and a plus charged carbon. Now, the question we want to ask is, all right, so now that we have this, what does this actually mean in terms of the reactivity of the acid? Well, let's think about these hydrogens and what we're going to have here. So what we want to think about is a ketone. So this is our ketone and this is our ester. The ketone is more acidic, meaning we're more likely to have this hydrogen come in sort of like this, right? So what is that actually going to do? Well, when we draw this, we're going to form this species, which is actually going to be something called an enolate. So you don't have to worry about that too much right now. It will come up later in the course. But what we'll see is that the reason why this is more acidic is because this is nothing stabilizing that plus charge, whereas here we have this lone pair on this oxygen, which will actually stabilize it, making it sort of less likely for the hydrogen to want to go down like that. Does it make sense? So it all comes down to a sort of stability argument. And in this case, the key bond is the carbon-oxygen bond. And that's what we want to focus on. Why is it less likely? Well, because if you think about this, right, this delta plus here is actually going to be greater than this delta plus. Because this delta plus is stabilized by the oxygen, and here we have no stabilization at all, right? And if you think about why the hydrogen wants to be taken, once it is taken, we have extra electrons. And these extra electrons are going to want to fill that extra positive charge. Does that make sense? Because it's essentially taking away a proton. But here you can think, okay, if it's already filled, right, it's already satisfied, it doesn't really need these extra electrons, and this kind of doesn't really have anywhere to go. Of course, it actually still does go like this. However, it is less likely. Does that make sense? Why it's less likely? It has to do with stability, a stability argument. Yeah, so whenever we're looking at this, we basically want to see how stable it is when we deprotonate it. So even here, if you think about it, when we deprotonate it, what we're going to form is this species. And the way I like to think about it too is that having two oxygens is better at stabilizing the negative charge, right? Because it's even, you can think of it with the inductive effect. Here we don't really have the inductive effect in play. All right. All right. So here we're going to have an alkene problem. Okay, so what part didn't make sense? Yeah, two oxygens are more stabilizing. Yeah. Yeah. So what's that called right now? What species we're working with? These are enolate species. You can see there's an ene, and then this is an all. It's an enol group, so it looks kind of like this with this proton. You will get to the reactivity of this later. Wouldn't that make the ester more acidic? No, okay, so when we're talking about stability, it's a bit weirder because there's different factors at play. So in this sort of case, we're fighting resonance versus induction. Okay, so notice how there's resonance here, and then there's also induction. So these two things are actually going to be competing for each other. So if we have something that looks like this, now the argument would be a bit different, right? So we would say, okay, now the induction is going to be stabilizing the negative charge a bit more. Sorry, withdrawing away the negative charge. But then because it's adjacent, we have to consider both arguments. Okay. So yeah, it is a bit of a weird answer. The truth is, in 233, they don't really get too in depth into the stability of resonance versus induction. So I wouldn't worry about it too much, because this question does go a bit deeper, and it has to do with orbitals and sort of how orbitals can stabilize negative charge as well. Does that make sense? Yeah, I'm not trying to confuse you. I don't want to go too deep into this topic. But later you will see with enolates, so ketones and esters, we will talk about enolates. So that's going to come later in the course, and we will talk more about the reactivity of these. But for now, just you can leave it as, okay, here we have no sort of stabilization from an adjacent oxygen group. So it's going to be more acidic. All right. Does that answer your question? Yeah, this is really good. So when you're taking OChem, organic chemistry, you want to be asking a lot of questions like this. This is super good. Keep asking questions like this, because if you understand why things happen and why things interact the way they do, you'll do really well in the course. So this is super good. Feel free to ask questions like this. It really sort of gets your brain thinking, and that's what they want you to do in Chem 233. All right. So for this question, we want to add a acid, and we want to add a water. So I'm going to pick the nucleophiles H2O because I know I'm adding an alcohol. And then I'm going to add some sort of acid, I guess HCl or H2SO4, whichever one you prefer. And again, we are going to make the most stable carbocation. So when we add the hydrogen or the proton. Now, so when you're drawing your mechanism, you can either draw the protonated water, or you could use the acid itself. Generally, I like to use a solvent because technically the acid will just be catalytic, so there'll be more of the water in solution. So we go like this, and we'll form the hydrogen as to this side, so that we form the tertiary carbocation. And then we have OH2 water coming in, and we will form this species, OH2, but now there's a plus charge. And what we can do is we can take a base, so H2O, to come in and take this off. And then we get this species, which is going to be our final product. So in this case, you might be wondering why they haven't included stereochemistry. And the reason why is because this is actually achiral. There's going to be sort of a mirror plane down it. And that means that it's going to be sort of a meso compound, which has no chirality. All right, we are done the session for today. So before we end, did you have any more questions that you wanted to ask? Just let me know in the chat if you have any more questions. Did you have any more questions? If not, we're done for today. All right, thanks for coming and thanks for asking questions.